So following the very exciting morning session on renewable financing and efficiency in oil and gas, we are now, and of course the wonderful lunch, so thank you Schlumberger. We have an even more eventful and exciting afternoon planned ahead of us. I'm very pleased to welcome our very first keynote speaker of the afternoon session, Dr. Holger Rubel from the Boston Consulting Group. Dr. Rubel is a managing director at BCG and the global head of BCG's energy and sustainability sectors. He has extensive experience in renewable technologies, energy efficiency, and carbon-related issues. And over his career has worked across different geographies, including Americas, Europe, and Asia. Dr. Holger holds a PhD in physics and mathematics from the universities of Heidelberg and Cambridge. So without further ado, join me in welcoming Dr. Holger Rubel.
Thanks a lot. Pleasure being here today. Well, today I want to talk about energy storage in the context of a changing energy landscape. And some people say we don't need energy storage. Others say if we have cheap, redundant energy storage, basically have saved all the energy problems in this world. Well, as usual, the truth is somewhere in between. And I want to talk a little bit today about the boundary conditions and business cases which might provide an opportunity for storage to become a successful business model going forward. So let's look at the facts. So why are we talking about storage? I mean, as you all know, we have an increasing penetration of wind and solar energy in many parts of the world. And unfortunately, both technologies don't provide a steady state of power supply. If it's windy, we have power. If it's not, we don't. And the same is true for solar. So we have to live with fluctuations. And of course, storage is one way to manage fluctuations. But there's also other ways doing that. There's not a golden bullet of how to change this and to manage this challenge. So we have, for example, conventional backup, how we can try to balance the fluctuation. It works, of course, technically. It is associated with CO2 emissions, typically. Of course, you can extend the grid. You have, if you take offshore wind farms, for example, in the North Sea, you have to transport energy from there to other parts in continental Europe, also even in the UK. And of course, you can leverage demand response as one means. Yeah? All have pros and cons, and storage, I think, is one part of the equation in order to solve the problem. So, I mean, coming from the volatile supply from renewables as a starting point, there's other boundary conditions that enable and make a business case for energy storage. We have changing electricity markets, and I will touch upon all those topics now in the presentation. Of course, technology is a very important driver because, I mean, storage today is expensive, and the cheaper it gets, the more likely is a further penetration of storage. We have issues with the grid, and storage can be a way to address grid issues. And many countries provide boundary conditions that enable a further penetration of storage. Some countries do, some countries don't. So let me start with the problem we have today. And this is one example. What you see here is a typical load curve. Germany is one example, but you can take any other country. A typical load curve in the year 2030. Yeah? And you have, what you see here is a typical supply of energy. The brown stuff is typically it's conventional must run. Then this is wind, the blue one, and then you have solar, the yellow one, and you see at some points of the day, you see that you generate more electricity coming from wind and solar than you can consume actually. I mean, this is a picture for 2030, but it even happens today. Not that often as you would suppose, probably in 10 or 15 years from now, but even today you have situations where you produce, especially in Germany, more electricity with wind and solar at some days than you can consume actually. And that's a challenge you somehow have to manage. Of course, you can throw away everything here, but it would be, I would say, economically not very clever to throw away everything because we have invested in those technologies and you want to draw a benefit out of that. So that's a challenge we have. And this challenge, actually, you can look at the complete value chain. If we start, for example, here at the generation side, I mean at renewables generators, the key what you want to achieve is actually to make renewables more baseload-like of a power generation. So you can use storage in order to somehow balance the fluctuations and make it more flat. And if you do that, of course, you don't have any curtailment and any other stuff. You can optimize the business case based on that. On the conventional side, if you take coal power plants or nuclear power plants, for example, I mean, today they're even used in order to ramp up and ramp down. It's technically possible. I mean, 10 years back, people even said, look, we can't do that. We can't just ramp up and down a nuclear power plant or a big coal power plant. You can do it, but the downside is, of course, you need to have more maintenance. It's just more pressure, more maintenance needed on the power plants. So one goal of storage, of course, can be, if you come from the generation side, to stabilize, to balance fluctuations, to increase the level of conventional generators, so the time you can run it, and also to make renewables dispatchable in some way. The next part of the value chain is about our grids. And if you look at transmission grid first, you see that in some countries you have some areas where you have a kind of focus areas of renewable generation. I mean, offshore wind is one example, with very massive installations of wind turbines in a gigawatt range. But also what you would call a distributed power generation. There are some areas in Europe where you have lots of rooftop PV, for example, and you have to transport the energy from places where it's generated to the places where it's consumed, and that's not always at the same place. And grids are not built for that purpose, so you would have to extend the grid. The same is true if you talk about the distribution grids. I think many of the renewable energy that we see in the future, in Europe especially, will be around distributed power generation, primarily solar energy. Rooftop solar, residential or on commercial rooftops. And the difference compared to what happened in the past is that you produce energy, of course, and you want to, of course, supply it to other places nearby. And the distribution grid is not made for bi-directional flow of electricity. Usually it's made that you can provide a certain amount of energy to your homes, but not, of course, providing a big capacity in order to transport it backwards. So this also puts lots of pressure to the grids. And I mean, there's some countries having good grids where this works easier, there are other countries having not so good grids where this is really a big challenge. And finally, we have the end users. In the past, end users invested into renewable energy, primarily solar, because it was a good business case. There was feed-in tariffs and other incentives. It was just a good way to earn money on that. But I mean, things change. Feed-in tariffs, other incentives go down. And I think the future investments on the residential side or for the end user side, commercial side, only will happen if there's a business case behind that which goes beyond feed-in tariff. And this is about self-consumption. I will talk about that later on. So there's quite some ways where storage can play and enable some of those things and enable new business cases that we haven't seen before. So let me touch on electricity markets. I mean, a typical development going forward that we expect to see, that you see here the retail prices, they are expected to grow. The prices are expected to grow. On the other hand, the wholesale prices are expected to decline because renewables, wind and solar have more or less zero marginal costs, so they pull out the other power generation assets out of the merit order curve. But you also will see that we have higher fluctuations. And higher fluctuations is good for storage because you can buy cheap and you can sell high. So it gives you, let's say, a business case for entering into storage. And then on the regulatory side, many markets start to open up for storage as well, so that storage assets can be used for balancing power, ancillary service, and other stuff. So we will see some new business cases coming up out of the electricity markets where storage can play a role. Then, I think which is very interesting is about technology, because technology is a key enabler about storage. What you see here is basically there's different application fields of storage. Central, so it's more kind of large storage assets you see within the transmission grid, for example. Then you have decentral storage, which is probably in buildings or close to buildings. And then you have kind of mobile storage, which is used in e-cars, more or less. And there's different technologies which are suited for those applications. And also here, there's not the one and only storage that takes it all. Depending on the application, there will be a coexistence of many storage technologies around. You see here, this yellow kind of stuff, mechanical storage. I mean, a very well-known technology is pumped hydro, pumped storage. It's reliable, it works well, it has high round-trip efficiencies. The problem is that you hardly find places where you can build such pumped storage. Yeah? You can do it in the Alps, for example, some other places, potentially Norway, but it's limited space. So it's good, but it won't solve our problem going forward. And then you have something like compressed air, which might stay a niche technology. And kinetic storage is something that you can use for probably frequency regulation because it doesn't have a high storage capacity. Here in the middle you see batteries. I think batteries is a very promising technology for storage. And I think for the years to come it will be the dominating storage technology because batteries are around. They are still expensive, but they are supposed to come cheaper. And again, the key question here is what kind of batteries will be the ones that will penetrate the market most. I mean, there's quite a variety of electrochemical batteries. I mean, you have lithium-ion batteries, and there's various flavors of lithium-ion batteries around. You have the so-called redox flow or vanadium redox flow batteries. And you have other so-called salt batteries like sodium sulfur batteries or sodium nickel chloride batteries. All of those technologies have their pros and cons in terms of power, in terms of storage capacity, and there will be coexistence of all technologies. But we believe that in the years to come, especially if we talk about decentral storage application, batteries will play the major role. And then we have hydrogen. Hydrogen is a very interesting animal. I think hydrogen will be the only storage technology, so to speak, that will enable long-term storage or even seasonal storage, because you can store a large amount of electricity in hydrogen and convert it back into electricity. I think it will take a while before it's becoming economically feasible because you need large electrolyzers in order to generate the hydrogen. But you have one advantage with hydrogen. Of course, you can store it in dedicated caverns or other tanks. But you also can feed hydrogen to some extent into the gas grid. And the gas grid is a huge storage. Yeah? And you can burn it with existing assets, gas power plants, for example. So in other words, you can use the existing conventional fleet driven by kind of green gas, by hydrogen. So that's the way which I think is the most promising one in the next years to come, and probably even more feasible than deploying whatever large hydrogen caverns where people also get nervous, like sitting on a hydrogen bomb or whatever, which is of course not true, but people think like that. So one word about technologies in storage. I mean, let me talk about lithium-ion a little bit. Lithium-ion, why is lithium-ion a promising technology? It's not because it is necessarily the best technology for stationary storage, but it has some scale, and the scale is coming from e-cars. E-cars tend to use lithium-ion technology. And with that, you have lots of scale, which drives the cost down. I mean, you all know the Tesla, so you saw Tesla standing around in front of the Tesla giga factory on batteries. I think this will drive the cost down, and also stationary storage will benefit from that. Of course, there's a little bit of a downside, I would say. Let's say something like that. For e-cars, you would use different kind of lithium-ion flavors compared to what you would need or ideally need for stationary storage. For e-cars, you try to maximize the energy content in the battery, so size plays a role, and you try to avoid that the battery is exploding once you crash the car. And this is how our batteries for e-cars are designed. For stationary storage, you don't need that. Space constraints is typically not a big issue, and you don't have any crashes at home as well. So you would probably use a different type of lithium-ion battery for stationary storage, but you probably won't get the scale you need in order to bring the cost down. This is why today you use a typical, let's say, e-car battery also for stationary storage applications, which is an advantage because you have scale in there. And this is why we expect also that the costs will come down probably by 50% in the next 5 to 10 years, which makes it quite attractive to look into some applications at least. And I will talk about one application later, which is about storage for residential applications in combination with PV solar. Other technologies also, of course, are supposed to reduce their costs, but I think until 2020, it will be tough to compete against lithium-ion. It will take some more years, probably 10 years or so, before Wedex-flow batteries become also an attractive technology, but for different applications compared to what we see for lithium-ion. Then, I touched the grid topic. I think grid applications will be a very important application fields for storage. And the main application will be to avoid the building of and the extension of grids. And I will also talk about one example later on. That's something which is already used today in many countries. For different reasons. Reasons can be, as I said, that grids are not built to transport in both directions. There's geographically some challenges. Some grids are old and not really made for, let's say, big loads that will be transmitted via renewable energy like wind and solar. So multiple applications in the grid. And finally, regulatory requirements. In a similar way as in the past years, wind and both solar have been subsidized by many countries in order to drive up the business. Yeah? In particular, solar was basically driven up by many subsidies we in Germany, come from Germany, we provided to the market. We helped scaling up the industry to a significant extent, yeah? Which helped, of course, to bring costs down. I think it needs a similar push also for storage to bring costs down. Some countries do direct subsidies into storage. In Germany, you get a 30% discount, more or less, if you apply it for residential storage. Other countries make it just compulsory. And there's also, of course, lots of indirect ways in order to manage storage. But there's also ways of trying to avoid storage. And this is just one example I want to make. It's about net metering. Net metering is something you have basically in every US state. And if you have net metering, you just don't need storage, because net metering is the perfect storage, at least from the perspective of the owner of the renewable power generation asset for solar or for wind, for example, because you just can use the grid as a storage. You feed it in, you have a smart meter counting how much you have fed in, and you're just pulling it back in the time you need it. So the point is, it's good for the owner of the assets, but someone has to pay for it, because you still have the fluctuations in the market. And this is going to be expensive the more people start to use net metering. And this is why I believe, and we see the initial signs on that some states in the US start really to limit net metering. At some point, I think they will stop it because it will be very hard to handle and will be too expensive to handle. And then again, we are back at the point where energy storage can play and will play a role in those states, like, for example, California is already doing. So having said that, there's lots of, let's say, boundary conditions that enable a good business case for storage. And before I move into the applications, let me probably start with that picture, because it looks a bit technically, but just to give you a feeling, when we talk about storage, it basically means we feed electricity in, we convert it, depending on technology, we store it in whatever form, and we convert it back into electricity. So we're talking about round-trip efficiencies of those batteries, typically, which can vary significantly from whatever 85% for batteries. It can be as low as probably 40%, even lower if you talk about compressed air, for example. And this is what I want to talk today. It's about electricity, and then using it in the stationary application fields. Of course, I also can use electricity for decent applications, which would be charging batteries for e-cars. Yeah? And there's also what I mentioned before, if we talk about hydrogen, various ways in order to utilize the hydrogen that has been generated out of the electrolyzers coming from renewable energy, and you can use it in chemicals or in other applications. Or you can use it even for hydrogen cars as one way of having green hydrogen for cars. So that's what we that's the background, and today I want to talk about applications in stationary storage. And there's three fields of business cases we looked at, and I think what is important when we look into storage in our research and our projects, we try to look from a pure business case perspective. So what makes storage attractive? Why are people investing into storage without any incentives and other stuff? So we try to look at the fundamentals and try to understand what is driving that. Of course, if there are subsidies and so on coming on top, it helps to accelerate the adoption of storage, but we want to understand the fundamental economics behind. And what we are doing is we take, of course, there's many parameters you can vary and try to understand. What we are trying to do is to understand coming from the cost of storage. So at what point is storage attractive at a certain business case? So let me start, and I do that as a deep dive later on, the PV plus storage, which is basically about increasing self-consumption at home, having a PV rooftop installed. And storage is a business case in order to increase the self-consumption, and out of that there comes a business case. We'll explain that later. Then we have, and I mentioned that, is about the grid. And the main business case for storage in a grid perspective is about deferral or avoidance of a grid extension. So what's behind that? I mean, let's say you have a certain area where you start building up onshore wind parks or a lot of, let's say, solar PV, and you have to transport it to other parts in your region. Once you have reached the full capacity of the grid and you build more, you're not in a position to transport the electricity away to other places. So then you have only two options. The one option is that you build a new grid so that you can transport the energy. The other one is to avoid, let's say, and to balance the peaks, because grids are always built to manage the peak flow of electricity. And if you can avoid the peaks by, let's say, if you take PV at midday, of course you have always a peak at midday. And if you can avoid shaving the peak a little bit, and using a battery for that, then you can still continue to use the existing grid. And there's a business case behind that, which is driven by, of course, in this case, the cost of storage. And it depends or calculates against the cost of building a new grid, which depends on, for example, how long you have to build the grid. And this makes also a good business case. And we see that in many countries, even in Germany, where we have, I would say, a fairly good grid, we see some communities building storage in a megawatt range in order to avoid building new grids, because it's easier to do. Building a grid is always a hassle. You have to, to build something. You have people not want to having the overhead transmission lines next to their homes. So it's always difficult to build grids. And this is why even advanced countries on the grid side, like Germany and some communities, are investing into the storage in order to avoid grid extension. And then we have, if you look to the very right, what I've mentioned before, how to make renewables kind of in a baseload type manner to make it dispatchable. Yeah? This is shown here. And I mean, what you can see here also for that one, there's always a business case which is a major, let's say, motivation of doing the business case. And if you want to optimize the business case for storage, you try to reap other, let's say, possible ways of income for your storage. This can be price arbitrage, what I mentioned before. You buy cheap, you sell high, so basically utilize fluctuations in electricity prices. And you can use it, for example, for balancing power. Yeah? So with this, you just improve your business case for the respective application. And the island grid or off-grid storage is a very attractive business case already today. Because today, in those locations, you use diesel power generators. And diesel power generators is a very expensive way of producing electricity. So having a combination out of PV and storage is always a good business case, yeah, with existing technologies you have around. Yeah? It always makes a good business case. And this is why, if you look now at the very bottom, looking at the target cost, so this is what we think is a kind of break-even cost of a storage or battery in order to make the business case attractive. And you see quite some differences here. So, for example, if I take the flexibilization of renewable, you need to have very cheap storage in order to make it an attractive business case. Why is it the case? Because energy markets don't pay today for balancing electricity a lot. This might change in the future, probably if you see capacity markets or other mechanisms, this might change. But today, this is not honored by a price premium. This is why you need to have fairly low cost of storage in order to make this business case happen. On the other hand side, what I mentioned, if I take the island grid example, you can afford a fairly expensive storage to make it attractive already, because cost of electricity coming from diesel generators is so high. And then we have some cases which are in between those two, which is the residential part, where you see something like 1,000 euro per kilowatt hour. This is a typical price we see today in the market for batteries. And for grid extension, of course, it depends a little bit on the situation, but would also be in a range a little bit below 1,000 euro per kilowatt hours. So this is what we're looking at, try to identify what is the kind of break-even points for storage costs to make business cases happen. And if we now look into penetration, what's happening in the market now, of course, this will follow these cost positions I've mentioned. So today we see already lots of, of course, we have demonstration projects all around, but those are not driven by economics. They're just, some investments, and people are not interested into real business case. So what we see today already is grid applications, off-grid applications in many parts of the world. Can be developing countries, but also can be countries where you have very remote places, or where you have a grid which is not very good. And even in the US, this is a very common application already. So the next wave will be PV plus storage, starting these days already in countries like Germany or Italy. Next wave will be around all the grid applications I've mentioned. Of course, here, again, it will be those grid that have, let's say, longer kilometers to bridge, whereas in rural or urban areas where you have not that long transmission lines, of course, the business case is a bit tougher. And in the end, we will see, coming in the very end, the pure balancing of wind or solar, because it's not a very attractive business case, and it will require very low cost of storage. So let me give you one example starting with that one, about the self-consumption, which is PV plus storage, and why this is an attractive business case. So what you see here is the following. You see here a typical load curve of a residential home, something in the morning, something in the evening. And what you see here is a typical PV production curve. Has a peak in the afternoon, of course, and nothing in the night, apparently. And without storage, of course, self-consumption depends just on this area. So where electricity generation is at least enough or even more than what you need. And in typical homes, you have without storage a self-consumption rate between 20 and 30%. But this is what you can use coming from electricity, from the utility. And why it's a good business case? It's a good business case because levelized cost of electricity coming from solar these days is about, I would say, between 10 and 12 euro cent. You can calculate it back into British pounds. And in some countries, like in Germany, you pay almost 30 euro cents per kilowatt hour from your utility. So you have a delta of almost between 15 and 20 euro cents per kilowatt hour that you save by using electricity from your own PV generated compared of what you have to pay for the electricity from the utility. So you want to use as much as possible of the electricity because it is a very good business case. Feed-in tariffs today are by far lower, in the range of 10 or 11 euro cent per kilowatt hour. So storage, of course, is a way in order to increase the self-consumption. As shown here, if you have a battery, you can use this kind of yellow stuff in order to fill up the battery, and you use it, you discharge it in the night. And with this, you can, if you take a typical use case, if you have a 4 kilowatt solar panel on the roof, you take a 4 kilowatt hour battery. So it's about 1 hour, full power. Usually you don't need 1 hour of full power at home. But with this, you can have a very good day and night bridging of electricity. And with doing that, you can increase the rate of self-consumption in a range between, I would say, 60 and 75%. And this drives the business case behind that. And let me go back to this picture here, where we have shown that, talking about grid parity. I'm sure you have heard about that. So what you see here is various costs of electricity for over the years for wholesale prices, typical commercial or industrial, and also for residential. It's not to scale, it's just conceptually. If we look at PV, costs of electricity coming from PV, you see, of course, it has come down quite significantly over the past years, and it continues to decline over the next years, not as strongly as we have seen in the past, but it's continued to decline. And those points are grid parity points. So in other words, at this point, cost of electricity coming from PV is as expensive or as cheap compared to what you would have to pay to your utility. And this happened, I mean, in this example, 2013. In many countries, it was even earlier. And a similar thing can also happen, of course, if you take commercial. It takes a bit longer because commercial electricity prices are typically cheaper compared to residential ones. But also in some countries, you already start reaching this parity today. Now, if you add storage to that, it's not for free because storage costs quite some money. In other words, it will shift this curve to the right. So in other words, it will take a bit longer in terms of years, because again, this is a cost curve over the years, before you reach the grid parity. But in many countries, Germany, Italy, 2014 or 2015 is just the point where we reach this break even, where a system out of PV plus storage is as attractive as buying electricity from your utility. And then things are getting interesting because then people think about, how can I really improve and make a good business case out of that and improve my self-consumption on that. And what we did, of course, is we looked into economics. And this is just one example, and we've done it for, of course, many cases, and I'll show you the outcome in a minute. So what you basically do is, how does a business case look like? You avoid, of course, the retail cost by self-consumption. Of course, you get a little bit lower feed-in tariff. It's not as high because feed-in tariffs are low. You have to pay for storage. It's not cheap, it's expensive. You have some OPEX in storage as well. You have to replace something, and then you have a business case. In this example, where we have assumed cost, I think it was 1,500 euro per kilowatt hour, it is not a good net present value. So you wouldn't do an investment into the business case. But if you now start to vary the cost of storage, you get a chart like that. So you see here the years, you see here the cost of electricity, and you see here this blue line is a kind of ISO curve where the net present value is 0. This means just pick one point. If you take a storage cost of whatever, let's take 1,000, which is expected to happen in 2019, the investment would give you a 0 net present value. For costs that are lower than 1,000, you would have a benefit by having a storage in your home together with PV. So you would earn money having a positive net present value. Now, if we now look at some real numbers, and this is shown the dark yellow or orange kind of color here. This is a typical what we expect as a price curve of batteries. And with batteries, I always mean a complete battery system. A battery, electricity management or energy management out of that, casing, everything like that. So we see probably we are now in 2014, it's a bit of 1,000. In 2015, we probably reach about 1,000. If you are clever, you can get it even cheaper. In other words, you're reaching now a zone where you actually are break even. So we are reaching, this is for German numbers, a point where people start to looking to investments with PV and storage. And as I mentioned before, what we're doing then is we look into incentives. And if there's an incentive like you get 30% with a off by KfW is let's say a government subsidy for, it will lower the price of electricity, of the storage, and lower the price of electricity and make storage an attractive business case. So based on that, you can see that this will be a main application we expect over the next years in many countries. Storage as increasing self-consumption, making a business case out of that. So coming back to technology. So I mentioned before there's quite some ways of building batteries, and there's 3 technologies shown here. It's lithium-ion, it's the salt batteries, sodium-sulfur batteries, and we have redox flow batteries. And we have shown here the applications I've mentioned before. Yeah? And you see 2 symbols. One is about this Harvey ball is about the technological feasibility. So can you use it technologically? And this green or yellow or red arrows give an indication about the economic attractiveness. So is it a good business case or not? And what you see is that lithium-ion is technically you can use it for, let's say, all kinds of applications. And for the residential part, it's the one that has also economically an attractive business case. If you move into grid deferral, grid management, other technologies might be even more advantageous compared to lithium-ion, for example, sodium-sulfur batteries, because here you use typically batteries in a megawatt-hour range, so fairly large batteries. And other batteries might have, not going into details now, but better characteristics technologically in order to build that, and it might be economically more attractive. And there's other applications, for example, if you take island grid or off-grid applications, where you can use all kinds of batteries. For hydrogen, just for example, it's something, of course, you don't use in those kind of business cases. Hydrogen is something you would use for large-scale storage, seasonal storage, or for feeding it into the grid, and into the gas grid. And it will take quite some years before it really is a good business case. So looking a bit into the market, we also have done a modeling of how we see the storage market developing over the next years along the various technologies. And here you see the market in monetary units, so it's billion euros. I mean, it's small today, it's on a global basis. The colors are the various technologies. And we expect that over the next 5 years, batteries will make more than half of the storage market, driven by the many decentral applications I've just mentioned before, because batteries are very flexible, easy to deploy, compared to other technologies, like, for example, if you take here pumped hydro, there will be some pumped hydro. It looks big, because if you do pumped hydro, it's typically in the kind of hundreds of megawatt or even gigawatt range. So it's huge investments, and it's just distributed over the years, and there's still some big projects around on a global basis, in Asia, for example, but not in Europe. And you also see here this light green hydrogen. It's a kind of a joker, because we also don't know how quickly technology is developing. Yeah? So you have to bring down the costs of hydrolyzers, electrolyzers in a, let's say, significant way in order to make it economically attractive. So it's a kind of a joker, but we expect that at least in 10 years from now, it will become a significant part of our investments into storage. So this is where I would like to finish, because I would also, of course, would be available to answer some questions, and of course happy for a lively and open discussion. Thank you.
Thanks. Very interesting. Tim Lyons from Orphan International. As you're going through those various technologies for storage, a couple of things occur to me, which is what's competing with storage here? So, politics willing, where would you plot east-west high-tension transmission on your graphs of costs? And where would you plot dual fuel for highly energy-intensive industries such as cement, steel making, and smelting?
Well, it's a good question. I think your first question on transmission lines, right? I think it really depends on the individual situation you have in a certain country. Yeah? There's some countries where if you really build, let's say, large offshore wind power farms, yeah, or large onshore wind power farms, at some point you reach such high amount of, let's say, power and energy that it's very hard to cover that with batteries. Yeah? You would have to build transmission grids. Because scaling up batteries has some limit. I mean, theoretically you can do everything, but at some point it's not getting really cost effective. So I think there will be a balance. I think on transmission lines, I think the storage is not a big competitor. It will be more about the distribution type of lines. And for your other questions, to be honest, I don't really have an answer. I just don't know it.
My name is Philip Hirsmans from Unicus. We are an intelligent grid and storage company, and whilst I agree with, I would say, 95% of what you just said, I have some serious issues. First off, I'll be brief though. I would like to know what a dispatchable must-run load is. But that in brackets, the issue, the biggest issue I have is that you see PV storage units coming before battery units in the distribution grid. And as you well know, probably, we just opened Europe's first commercial battery power plant. We're commissioning one that's very near to commercial application just now in Leighton Buzzard. Aren't you just being a little overly optimistic also at the same time on the residential part, because you don't take into account the grid stress that dumb, and by that I mean in storage, that does not talk to the grid, will produce? And aren't you just taking what they were saying in the panel before, blocking out potential regulatory intervention that must come if there's a large-scale uptake of this? Thank you.
Yes, thanks. A very interesting question. Of course, I know your company, and having done lots of discussions with colleagues of you, I think talking about the PV plus storage, I mean, there's what I show here is about the basic business case behind that. Of course, there's some challenges in order to adapt it to large scale, and there's, I think, multiple challenges. I think the one thing is about what I mentioned. If you have this grid parity, we call it storage parity. I think this is a necessary requirement in order to make the business case happen, but it just doesn't come alone. If you look today, how people have or used to invest into PV, it was like bringing money to a bank. You know, it was the state guaranteeing for the feed-in tariff, stuff like that. And we have built, especially in Germany, a large economy based on that. You know, lots of installers, you know, all kinds of stuff. If we now start about PV plus storage as a business case, it's completely different, because this is not subsidized by the government. It's about that the investor, the homeowner, has to think about its own business case. And this, I think, is a big challenge, because you have to convince customers or the end users in a very different way compared to what happened today. You have to re-educate installers. You have to re-educate also banks who might give some loans, yeah, which happened in the past. So I think it will take quite some years, 2, 3, 4 years, before it really picks up. Yeah? But the point I want to make is about the fundamentals are there, but people need to be educated. You need to explain it to them that it's a business case for that. That is one thing. The other thing is about regulatory intervention. I mean, if you look today, what's happening if you use increased self-consumption? I think the first thing is you use less electricity from the grid. So I believe that you don't put strain on the grid, because I think the best that should happen is the place where you produce electricity and where you use it should be a very good thing, because you don't need any grid for doing that. This is why I think, compared to today's situation where you build up electricity, PV, and feed electricity in the grid, this puts strain on the distribution grids, and many of those grids is not in a position to capture this. If you, of course, can manage to, for example, to balance out the peaks of PV, what you see today, by storage, it will release strain from the grid. So I think it's advantages for the grid if you don't do that. The other point is, how are grids being paid today? And grids are being paid today as part of the kilowatt-hour fee, in many countries at least, as part of the variable fee. So now if you start doing self-consumption to a high extent, you don't, of course, buy electricity from the grid. In other words, or from utility. In other words, there's less money left in order to provide investments from the grid operators in order to maintain or even build the grid. So at some point, you are right, there might be a situation where the government will have to think about what's happening if everyone is doing self-consumption. Who is then paying for the grid if no one is actually, or only buying grid to some, let's say, in some parts of the day or part of the year. And I think this is a very good discussion, because this will lead to some regulatory ways of how one can finance a grid. But I think there will be a balance on that, because the one way is that you increase the fixed price. So you have to pay a fixed price for the grid. But if you make the fixed price too high, people are not interested in saving electricity anymore. So there will be, we can't just, raise the fixed price of electricity in order to cover that, because then people are not incentivized to save electricity. It's not very economically in the end. Yeah? And people that are using lots of electricity would be privileged compared to others, would have to pay a lot of money for the fixed fee and not using much. I don't have an answer for that, what's going to happen, but I think there needs to be a balance on that. But fundamentally, I believe it will not change the business case. It might defer the business case by 1 or 2 years, because costs will come down, but it won't completely make the business case unattractive at all for, let's say, forever.
Thanks. Möller Son, MBA student here at London Business School. Just 2 quick questions, please. The first one is on the technology side. I think you used the lithium ion as your base case for a lot of the analysis. Just wanted to get a kind of your reasoning behind, and also especially with regard to the potentially cheaper but maybe less advanced technologies such as lead acid. What do you think the potentials are for them? And the second question is regarding capacity market. You kind of briefly touched on that. I just wanted to get your view on how you think the introduction of a capacity market can impact the kind of economics around battery storage in the longer term, especially if, say, the capacity mechanism attracts a lot of the thermal powers back onto the capacity market. Do you think that would kind of put a threat onto the development of energy storage?
Mm-hmm.
Thank you.
Thank you. Let me start with the first question about technologies and why we have used lithium-ion technology as a base case, because I think we wanted to make things comparable, so we used, let's say, one technology and did all the calculations on that. And the business case in the end doesn't depend on technology, it depends just on the cost of the technology. So you can use any other technology and say, look, if there's a certain cost for other batteries, you can also, of course, realize the business case. On lead-acid batteries, we haven't looked at it because I think, depending on the application, lead-acid batteries are probably cheaper on the first glance. But if you look on how many cycles a lead-acid battery can do, and if you look about, let's say, a 10 or 20, typically you look at the 20-year life cycle of such an investment. And if you have to replace, a lead-acid battery has probably, it depends, 1,000, 1,500 cycles, whereas very advanced lithium-ion batteries might have 5,000, 6,000 cycles, some claim even more. You would have to have, 4 times the same reinvestment for lead-acid compared to having one lithium-ion battery. And if you put this in the business case, you really realize that it's not so attractive anymore in the future. And also, I mean, if you talk to, let's say, a self-consumption business case, people want to have something plug and play and not being exchanged for 20 years. And if you have exchanged everything, you like lead-acid is a car battery, everyone has a car battery which breaks every now and then. You just don't want to have it at home. Yeah? So this is why I believe lead-acid battery is not a good use case, at least for residential applications. Of course, there's other ways of technologies, and I can't go into details here. And we have in detail investigated and also did lots of work for other technology firms. There's other technologies outside, apart from lithium-ion technologies, that can be used, various types of salt batteries. Some of those are commercially available, others are more in a research stage or pilot stage. But I still believe that the cost curve overall will come down for all of those technologies. Yeah? I think lithium-ion has just currently the best starting point in order to reach a scale. Yeah? Because the other technologies, you have some salt batteries or others, have the potential to reach a similar cost position, but you probably don't have the scale that you have for lithium-ion because from the e-car, if e-car really at some point will happen, it will bring down the cost of lithium-ion as well. But technologically, lithium-ion is probably not the best technology you can imagine. It's just around, and it's available, and the cost curve is for next years is there. Yeah? Your second question on capacity markets, I mean, this is a very good question. And to be honest, I mean, I don't have an answer on that because it really depends on how regulatory-wise you design capacity markets. You can have special, you can treat a battery also as a generator for providing capacities. You could even make a capacity market where you provide different conditions or different advantages for batteries compared to, as you said, fossil power plants, because you don't want to have your old fleet sitting around and producing CO2 like mad. So I think the governments, the regulator can design it in a way that batteries have a good position. Of course, they also can design in a way that they don't have a good position. It's hard to say. Yeah? And in my discussions I have with many regulatory bodies, I mean, there's lots of discussions ongoing. It's a complex system. And I think it will take also, governments have to learn to iterate regulatory boundary conditions because also the technology and price developments are changing very quickly. So you have to adjust also very quickly from regulatory side. Something that didn't happen in the past, if you look into the quick development or the steep development, cost development of PV, for example, the governments couldn't even react that fast in a way the costs were coming down. And then things happened like we saw in Germany, that people started to build PV like mad, just using some advantages because the government didn't realize that they had to reduce the feed-in tariff. And this is why governments need to be more flexible, need to learn what works, what doesn't work, but they also, of course, have to set some boundary conditions, what is important for them, which is security of supply. It's about what kind of CO2 targets do I want to achieve, what kind of costs are willing and able to afford from energy system. All those things they need to keep in mind and then derive the best regulatory system out of that, which is a very complex question in the end.
Thank you. David Buchan, Oxford Institute for Energy Studies. Are there any restrictions on storage arising out of the on the owning and operating of storage, arising out of the unbundling provisions which the European Commission has more or less required of the whole of the European electricity industry? Where does, in this sort of chain of generation, transmission, and distribution, and the fact that you can't own all three, or
Yes.
operate all three,
Yes.
where does storage fit in there? Is it a problem?
Yeah, I think you can think of business cases where this is really a problem. Yeah, especially I think you don't have a problem today if you talk about self-consumption. It's working. You might be forced to pay some fee for that, and we had some discussions in some country that you have to pay some additional, whatever kind of fee if you do self-consumption, but principally it's allowed. I think the biggest challenge is around that area here, so how to work with storage as part of the grid, yeah? And also business cases where you probably try to, as an operator, instead of putting, let's say, a battery into each home, kind of small-scale battery, economic, of course, it's more feasible to take a larger battery and you try to combine various homes with PVs on top of it, because then you can, of course, better, bundle the various fluctuations into one battery. Of course, it's cheaper to buy one large battery compared to many small batteries. And for those things, I think it's difficult to find a good business case on regulatory business case on how to handle that. Yeah? That's what we have learned. And it depends very much, of course, on the countries. And there's other requirements like what kind of metering do you need in order how to measure it and so on. Are you allowed to, if you make contracts with the customers, if you make 10-year contracts, is it allowed to do, or is it not allowed to fix customers to a contract for 10 years and not being able to change? I mean, there's many things which I think are not clarified currently, the kind of gray area. And also that's something where the governments have to make some clarity in order to even enable more business cases as we have seen here, which are the fundamental ones, but there's more of those that are economically more attractive but would require more complex regulatory boundary conditions, let's say it like that.
Okay, ladies and gentlemen, I think we are running a bit overboard on time over here. It was a fantastic presentation from Mr. Rubel, and thank you very much for coming to the Global Energy Summit. Thank you.
Pleasure, thank you.